Hello, in this video we'll do a few examples of using integrating factors. So you'll recall from the reading that if you have a function, a differential equation in a linear differential equation in the following form, then the integrating factor is given as e to the integral of p of t dt. Okay, so you're integrating the function in front of y. So we'll start with our first example here. Okay, so the first example we'll do is we're going to solve the differential equation y prime plus 2 over t times y is equal to cosine of t over t squared. With the initial condition, y evaluated at pi is 0, and we are restricted to the interval t greater than 0. Okay, and that's primarily so that we don't run into that discontinuity. Okay, so when you're solving, this particular differential equation, because the terms are undefined at t equals 0, you have to choose either t greater than 0 or t less than 0. Greater than 0 is the obvious choice. Anyway, so we'll start by calculating our integrating factor here. So it's e to the integral of 2 over t dt. Okay, so this is e times 2 to the natural log of t. Now, I don't need the absolute value symbols because I know that t is positive. All right. Furthermore, what I'm going to do, and you're going to see this kind of stuff a lot, so if you get a natural log in the numerator, what I can do is I can use the rules of exponents to bring that 2 inside. So it's really t squared. So again, I wouldn't need the absolute values even if t was negative, because the squaring would eliminate the negative sign. And then this guy is simply t squared, because the e and the natural log go away. All right, so when I use this integrating factor, my equation becomes t squared y prime plus 2ty equals cosine of t. Okay, and the whole point of this integrating factor here is that this side, the left side now, is the derivative with respect to t of t squared times y. Okay, you'll notice that the first piece, the t squared, is the first term, and then y prime, so it's first times the derivative of the second, plus the derivative of the first times the second function. So what we see on the left side is simply the product rule. Okay, and that's what the integrating factor technique is designed to do. You basically convert this into a product rule problem. Okay, and then what I'm going to do is I have this guy, and I'm going to be taking the antiderivative of each side. Okay, so the idea is that we have these two things, and we want to think about them being as like this equation is saying the derivative of the left side, or the equation represents two derivatives, and we can think of the right side as being the derivative of what? The sine of t. Okay, now you wouldn't normally write it out like this, but this is just like some more stuff, kind of reviewing what the reading talked about. So the idea is we're taking our basic equation, this guy, and we're kind of converting it into an equation about derivatives. And then there's a theorem from Calc 1 that says if two derivatives are equal, then their functions are equal up to a constant. Okay, so here are the two derivatives. These are the two functions, and they must be equal to each other up to a constant. Okay, so in other words, they must have the same antiderivative, again, up to a constant. And these are the antiderivatives. All right, and then the final step, and it's very important that you have the plus c here. Okay, so the second you remove derivative symbols, take antiderivatives, integrate, however you want to think about it, that plus c better be there, because in the next step, we're dividing everything by t squared. Okay, now that's okay, because t is positive. Okay, from the original part of the equation. Okay, so since t is positive, I'm allowed to divide by it because it's not 0. Okay, and then this becomes sine t over t squared plus c over t squared. Okay, so now we'll come back up here. All right, and we're going to apply our initial condition, which is if I evaluate everything at pi, so we would have sine pi over pi squared plus c over pi squared. This is all supposed to be 0 according to our initial condition, but the sine of pi is 0, so this is really saying that c over pi squared is nothing, which means that c is nothing. Okay, so the particular solution we're looking at, y of t, is simply sine of t over t squared, where t is greater than 0. Okay, so this is the particular solution. This piece back here, this is the general solution. Okay, Paul calls this the actual solution. But most of the time, you're like in a lot of textbooks, you'll see this as the particular solution, and that's how I'll refer to it most of the time. Okay, so anyway, so that's our first example. We found the integrating factor in the beginning. We multiplied both sides, and then we basically undid the product rule through integration. Okay, and then we used the initial condition to find the value of c. We'll be doing that process in every problem in this section. So for our second example, we're going to start by taking a look at this equation. Okay, so we're looking at the different equation 3y prime minus 2y equals e to the minus pi halves t. Okay, so we're going to use MATLAB to produce a direction field just to see what it looks like, and to kind of illustrate some of the stuff that you'll have to deal with. Okay, so now when we go to solve this by hand, which we will do in a little bit, you can't use the integrating factor when there's a 3 in front of that y prime, so we will have to divide all these terms by 3. Okay, now when we're doing things in MATLAB, we're going to do exactly what we did in the direction field video. We're going to use mesh grid, but then when we compute the rise portion of it, okay, the actual direction of the vectors, the function has to be solved for y prime. Okay, so this is like kind of specific to finding direction fields and stuff like that. You know, doing this by hand requires having this part on this side of the equal sign. But when we're in MATLAB, we need everything else to be on the right side except for the y prime part. Okay, so anyway, this is the equation solved for y prime. We plug that in. That's the rise part. Remember, run. The horizontal component is always 1. Okay, and I'm using the technique where I'm going to divide by the length. This dividing by L on the two pieces creates unit vectors. And then I'm scaling them by a half so they don't run over each other so much. Okay. Again, axis tight just makes it look nicer. It gets rid of the white space on the outside. Okay. So again, pretty hard to see with all those vectors, but if I full screen it, you can see what's happening. Now, the reason why I want to do this is because there is some distinct stuff going on here. First, you see all of these things. If you were to start up here and trace it out, they're all going up to positive infinity. Okay. All these arrows are pointing up, but all the ones down here are pointing down. So somewhere in the middle, it needs to change between stuff that goes all the way up and stuff that goes all the way down. Okay, and there's definitely, it looks like, horizontal stuff in here too. Okay, so there's going to be a solution that eventually becomes completely horizontal and stays constant. All right, so ideally, we need to come over here and figure out where that changes. Okay, so these guys are facing up, these guys are facing down. Maybe somewhere in here, it looks like, is where it switches from arrows that go up, from arrows that go down. And this is at t equals 0, so this is the initial condition. So what we're going to do is we're going to solve this by hand and look at which initial condition divides those two behaviors from each other. Okay. Now let's turn to our second example and work it out by hand. We've already seen in MATLAB a picture of the direction field, and we know that the behavior of the solutions for this equation are going to change their end behavior depending on the value of a. So what we're going to do now is solve this equation by hand using the integrating factor technique and locate the exact value of a for which the end behavior of this function changes, or the solution rather. So anyway, the first thing to understand is that we can't use the integrating factor technique the way the differential equation first appears because it only works if the function starts out y prime plus other things. Okay, so we got to get rid of that 3. So the first step is to divide all the terms by 3. And if we do that, we'll have this equation. Okay, then the integrating factor is e to the integral of minus 2/3 dt, which is e to the minus 2t thirds. Okay, so we would multiply everything by that. Okay, note that you can use the properties of exponents to put these two guys together. I'm not going to mess with it too much. Okay, I'll just put it together like this. Okay, of course you could add that fraction together and make it look nicer. Well, maybe I will. Okay, it's useful to have it like this for one thing, not useful for another. So we'll see. If we add these two things together, it becomes 3 pi plus 4 over 6. Okay. So anyway, so now that we've multiplied by the integrating factor, we can note again that this side is really a product rule being applied to this function. Oops. Sorry about that. 3 pi plus 4 over 6. Okay. And so this function, the antiderivative on this side, must be equal to the antiderivative of the other side. And the antiderivative is of course the integral. Okay, so if we integrate this, we have the 1/3 here. When I integrate that power, I'm going to get minus 6 over 3 pi plus 4 e to the minus t. And then actually here I'm going to split this up again. Okay, so you get the same exponential equation, but now I'm going to write it back in its original form. And you'll see why in a second. Okay, so it's no longer useful to have that together, but I did integrate, so I need that plus c there. Okay, so then the next step, as in the first example, is to divide everything by the thing in front of y. So the general solution then is going to be, and I'll do a little bit of simplification here, so this is minus 2 over 3 pi plus 4. When I divide by e to the minus 2t over 3, it cancels the one on this side, which is why I split it up again. So really, we just have this guy. And then when I divide c by it, I can bring it up into the numerator by changing the power to a positive exponent. All right, so there we have the general solution. Now, we had an initial condition, y of 0 is equal to a. Okay, so we want to come back down here and apply that initial condition to see what the particular solution is. So if we plug in 0, we'll have that plus c is a. Okay, and that implies that c is a plus 2 over 3 pi plus 4. Okay, so the particular solution that we're looking for here is minus 2 over 3 pi plus 4, e to the minus pi t halves, plus a plus 2 over 3 pi plus 4, e to the 2t thirds. Okay, so there's two terms here, and the end behavior is describing the limit of this as t goes to infinity. So what is the limit as t goes to infinity of this thing? Okay, so let's just think about this. There's two terms there. What's going on? Well, the first term, they both have exponential functions in them. The stuff in front of them is just a constant. Okay, so the first term there, it's got an exponential function, and that function has a negative power. So if t gets really big, that's going to get super small. Okay, and that first term just goes away. Okay, so that first guy there is going to limit to 0. Okay, so this thing right here is going to go to 0 because of that negative exponent. Okay, now what's going on with the second term? Well, that exponent is positive. So as t goes to infinity, that exponential function on the end there should go to infinity. But we have this this value of a in that coefficient in front. Okay, so what we need to do is we need to think about what's going to happen to that coefficient. So what's the deal? So what happens to a plus this thing? Okay, well, we basically have three cases. Okay, if this thing is a positive number, so if a plus 2 over 3 pi plus 4, if that thing's positive, then that whole term is going to go to infinity. Okay, then a plus 2 over 3 pi plus 4 times e to the 2t over 3 is going to go to infinity as t goes to infinity. Okay, because remember, the exponential function, that just goes to infinity no matter what. So so if the coefficient in front is positive, it goes to positive. The whole term goes to positive infinity. If, on the other hand, this thing is negative, then what's in front here is some negative number. Okay, a negative number that's not changing. It's just some constant. So it could be like negative 5 or something. Well, okay, negative 5 is pretty unlikely. Negative some decimal thing. Then this thing's going to go to minus infinity as t goes to infinity. Okay, and then the final case, okay, and this is the idea. So if this thing is 0, okay, then that term is 0 all the time. So this thing is constantly 0, which obviously goes to 0 as t goes to infinity. All right. So so the idea here is that this third case is the transition case where it switches behavior. So the idea is that the solution changes behavior when a is negative 2 over 3 pi plus 4. In other words, the value of a that makes that coefficient equal to 0. Okay, and that function is going to separate the solutions that go to positive infinity from the solutions that go to negative infinity. It itself will converge to 0 because the first term and the second term then will go to 0. Okay. So what we're going to do now is go back to MATLAB and show you guys how to plot these graphs, plot some sample solutions so you can see this in action. So we're back in MATLAB. We have the code for the direction field. Now we're going to actually introduce some new commands in MATLAB to show you how to solve differential equations, and then we're going to graph the results, okay, to show you where those behaviors are splitting. So the first thing we're going to need to do is solve the differential equation. I'm going to store the answer in sol, and the command is dsolve. Okay, so what we're going to do is first, dsolve takes 3 arguments. The first one, and they're all strings. The first one is the equation. Okay, so when we're doing this, so this is solving the differential equation. So when we're doing this, there's some special notation that dsolve uses. So y prime is written as dy, and y double prime is d2y. Y triple prime is d3y, etc. Okay, so that's special notation. So when I come in here, it's going to be 3 times y prime dy minus 2 times y is equal to the exponential function with minus pi t over 2 in it. Okay, so there's the differential equation. You could use this form or the form with everything divided by 3, but it doesn't matter to MATLAB. Okay, so the next thing we're going to do is put in the initial condition. The initial condition was y of 0 equals a. Okay, so we're just going to use the base example, and then I'm going to tell it what the independent variable is called. It actually assumes that t is the independent variable automatically, but I'm going to specify it. You would have to put x here if you wanted to use x. Some books do that. Okay, so anyway, so I'm going to do that, and I'm going to try to have MATLAB simplify the answer. Okay, and I wanted to print it out, so I'm not going to semicolon that. So if I do that, if I run it, it's going to produce the graph again. There it is, okay. And we see here, this is the answer we got before. Here is that constant term there, or that coefficient that we were talking about in the problem, okay. So what we're going to do is we're going to graph a bunch of solutions for different values of a. Okay, now if we come back here and I just wanted to kind of come back and say what is that that value, okay. Now the special value of a is 2 divided by 3 times pi plus 4, okay. I just want to see what that is about equal to. So it's about negative 1 point, negative 0.15. Okay. So what I'm going to do is I'm going to first show you how to draw a bunch of different graphs. Okay. So what we're going to do is we're going to use a for loop, and we're going to iterate through. Let's say this. Okay, so these are going to be the different starting values of a. Okay, and so what we're going to do is we're going to do that, and then we're going to use, we're going to need a hold on command. Okay, so I'm going to put that there because I'm going to want these graphs to be done over top of the direction field. So now I'm going to use the command fplot. I'm going to turn this into an implicit or an autonomous function in MATLAB. I'm going to do that using the eval command. Okay, so this would be the normal thing. I'm also going to specify that I want these graphs to be in red. Okay, so this is kind of like the plot command, except it does it with functions. This tells MATLAB that the function is going to be a function of t. This command's needed because sol is a symbolic argument, and fplot needs autonomous functions. So this just says to evaluate this expression using this variable. Okay. Now, what I need to do is I also need to include something here to tell it to use this value in place of a. Okay, so the command is subs for substitute. I'm going to substitute into solution. I'm going to replace a with I. Okay, and that should do it. And I'm going to need to change the axis back to this original thing. So I'm going to want to go from 0 to 5 with the x's, and then minus 5 to 5 with the y values. Okay, so let's see how that looks. Make sure we did that right. Hopefully this doesn't give me an error. Oh, no, it didn't. Okay, so there you see all of the graphs starting at the different values, the different whole number values, and how they look. They better follow the arrows. Okay, each of those vectors is supposed to be tangent to the solution at that point. Okay, so that looks good. But I also want to include the graph at the special value of a. So we'll do. I can do that here. Okay, now you got to be really careful here. When we're putting in that special value of a, it was minus 2 divided by 3 times pi plus 4. Okay, now the thing you have to be careful of is that when you type something like this into MATLAB, it doesn't treat pi as the symbolic value of pi. It treats it as 3.14, etc. And so it's not going to cancel this perfectly unless I tell it that it's the symbolic version of pi. Okay, so sim is the command that you use in a line of code to convert this to the symbolic form. Okay, so this is going to make this the symbolic expression that's going to go in here, which is then going to cancel that to 0. If you don't include that, it treats this as a fraction that's really close to the correct value, but not exactly equal to it, and so it won't cancel this coefficient out. And so it still goes to infinity. But anyway, so if I do this, and I'm going to want to be able to see that, so I'm going to plot that in green to distinguish it between the other graphs. Okay, so there you have it. The green solution, notice that it does curve up a little bit at the beginning, but then eventually converges to constantly 0. Okay, which is what we expected when we solved it by hand. Okay, everything that starts above that value will go to infinity, sometimes really slowly, but it does eventually. And everything below, even though it curves up a little bit, is going to eventually go down. So something that starts right here is probably going to have a local maximum somewhere in here and then eventually curve down to 0. Okay. So anyway, the purpose of doing this was to first show you how M behavior can change depending on the initial value, and give you an idea of how to use fplot to plot some sample solutions along with the direction field. Okay, and this is a really good way to use MATLAB to check to make sure that you plot both things correctly. If you did them both correctly, your direction field should produce vectors that are tangent to your solutions, and so you can use that to determine if you coded the stuff right. All right. So anyway, so that's it for example 2. We'll end this video with our third example. Okay, we're going to solve the equation y prime equals 1/2 y, y prime plus 1/2 y equals 2 cosine t, with the initial condition y of 0 equals -1. And after we find that, we're going to find the first local maximum of this function, which can actually be done by hand. We're going to need to use MATLAB or like a graphing calculator or something like that to do that. All right, so we'll go to MATLAB to show you how to do that. All right, so the first thing we'll do, like all the other problems, is find the integrating factor. Which is t over 2. Okay, then we will multiply everything by that. Okay, and the idea is that when we integrate both sides, this side's going to be e to the t halves y, and this is the integral of 2e to the t halves cosine t. Okay, now an issue that you're going to run into throughout this class is the need to know how to integrate lots of different things. Okay, so this class is really going to test your skills from Calc 1 and 2. This, if you recognize it, is a problem from Calc 2 that involves double integration by parts. Okay, so I'm going to do that off to the side. Okay, over here. So this is the integration. Okay, so I'm going to integrate 2e to the t halves times cosine of t dt. Okay, and the integration by parts, we're going to start out with u equal to 2e to the t halves and dv equal to cosine of t dt. Okay, so v is sine of t, and du is e to the t halves dt. Okay, so integration by parts tells me that this is uv minus the integral of v du. Okay, now I need to use integration by parts a second time to do that second integral. So that's what I'm going to do here. dv was the sine term. And sine integrates to minus cosine. Okay, so here was time number 1, here was time number 2. So putting this together, so then that integral is replaced by uv minus v du, so the extra negative will make this a plus now. 1/2 e to the t halves times the cosine of t dt. Okay, so so now we're just going to expand this a little bit, simplify things. Okay, the idea is that this integral that's on the left side is the same as this integral on the right side, so I'm going to combine those two pieces together. If I do that, then I will get, let's see, so there's 2 from the original piece, and then I'm going to add the 1/2 to it, so I will get a total of 5/2 times this integral is equal to 2e to the t halves sine t plus e to the t halves cosine t. Okay, so the integral is equal to 4/5 e to the t halves. Ooh, there was supposed to be a plus c here. It doesn't matter if I put it there at the very end, as long as you have it somewhere. Okay, so yeah. Now let's take this information and bring it back to the original problem here. Okay, so first notice that the integral we just calculated, we need 2 times that integral. So we're going to multiply everything here by 2 when we put it in. Okay, so we'll have, let's see, e to the t halves y is equal to 8/5 times e to the t halves sine t plus 4/5 e to the t halves cosine t plus c. Yeah, okay. You may have noticed when you were doing your reading and stuff that normally you just keep reusing the letter C for arbitrary constant. Technically, the C I just wrote down is different from the C over here. This C is half of what this C is. But, you know, if it was arbitrary to begin with, 2 times that number is still can be anything. So we just reuse the same letter over and over again normally. Okay, so we have that. Anyway, let's kind of block this part off. Okay. And now we'll find the general solution by dividing everything by e to the t over 2. So we have 8/5 sine t plus 4/5 cosine t plus c times e to the minus t halves. Okay, because we're dividing by that number, that's why the power turned negative. Okay, so the final step is to apply the initial condition, y of 0 equals -1. Okay, so if I plug 0 in here, sine of 0 is 0, so this is 8/5 times 0. Cosine of 0 is 1, so it's kind of non-trivial here, and then this is c times e to the 0 is 1. Okay, and this is supposed to be, what was I already forgot? -1, okay. -1. Okay, so then c is -1 to -4/5, which is -9/5. Okay, so the particular solution we're talking about is 8/5 sine t plus 4/5 cosine t minus 9/5 e to the minus t halves. Okay, so anyway, what we're going to do now is turn to MATLAB to calculate the first local maximum value here. Okay, which is going to require us taking the derivative of this and then finding when the derivative is 0. Okay, differentiating this can be done by hand, that's not a problem, but solving the derivative of this thing equals 0 is not something that can be done by hand, okay, because of the sines and cosines and the exponential function combination. There's no analytic way to do that, so you have to use a calculator or MATLAB or something like that. So here we are in MATLAB. We already have the solution set up here, and I'm going to plot it. Okay, so there's the way the solution looks. Now, I didn't need to do the autonomous function here. It actually takes, fplot does take the symbolic thing. As compared to the last example that we had done, that was because I used a substitute command that I needed the evaluation thing and stuff like that there. Okay, so if you already have the particular solution, like I already typed in the initial condition that gave me a particular solution, then it just does this normally. Of course, I could have put the at t and then the eval part here, and it would have done the same thing. Okay. In fact, I'm going to actually need that down here. All right. So what I'm going to do now is I'm going to differentiate it. The command for taking the derivative is called diff. I'm telling it to differentiate sol with respect to this variable. Okay, now I've defined everything's a string right now because I haven't declared symbolic variables. It's just easier to do it that way so I don't have excess lines of code. So here's the derivative, and now what I'm going to do is I'm going to use the command f0. F0 actually does require this part here, and what that does is allows me to approximate a root of a function, okay, where the function's equal to 0, and I'm allowed to specify around the value that I want it to look at. Okay, you can use the command solve. Okay, this will try to solve this, but this is the symbolic solver. If it can't solve it symbolically, it gets upset. Okay, so here's solve getting upset. It says it can't solve it symbolically, so it numerically approximates the first root that it can find, which happens to be the one we want. That's great, but sometimes it doesn't find the one that you're looking for. For example, if I wanted to know what this one is, okay, the second one, solve can't find that, and that's why we use f0, because it allows me to specify the location of the root I'm looking for. All right. Now, in order to use f0 properly, that's why I actually needed the graph, okay? So I'm looking here, and I'm seeing that this is, well, okay, well, that's not very descriptive. Here we go. Okay, so here, that 0 is a little bit after 1. This one is closer to 4. Okay, so so notice here when I run it, okay, this is the f0 one. It did match the solve command. Okay, so S0 finds the one that's closest to the number I put. If I want it the one closer to 4, I can do that. Okay, there's the one that's closer to 4. Okay, you just need to tell it where to find it. Okay, and so what I'm going to do is that's the x value. Okay, so let's call that x. All right, and then what I'm going to do is find the y value by taking the solution and plugging x in. Oh, this was supposed to be a t. Now, let's see if MATLAB lets me do this without using eval and subs. Uh, okay, yeah, it didn't like that. So what I'm going to have to do here is evaluate. So I'm going to plug it in, oops, to t, like that. Let's see if it enjoys what I did there. Yep, there it is, okay. So yeah, so that's basically it, okay. And I can make this, print out nicely, okay. So I didn't need that. So print f. So the first local maximum is located at that point. And the numbers I'm going to put in here are ty. Okay, so it's going to find it, and then it plots the coordinates of that first maximum, which, if we zoom in here, basically match what we're looking at. Okay, so yeah, so that's pretty exciting.